Hi everybody, this is the MATLAB and Simulink Racing Lounge. In today's session I'd like to introduce you to a method how you easily can determine chassis stiffness just using MATLAB. As some of you might know, I'm working at Formula Student Germany as a judge, and what came to my mind when asking you guys about your FE calculations, how you did determine the chassis stiffness, I asked some questions. And what I've seen, some of you are not really sure about the boundary conditions they applied, they are not really sure about the results. And this created the idea that I say, okay, I'd like to introduce you to a really lean and powerful method to calculate the stiffness of a truss framework. And your steel tube frame is nothing but a truss framework using the direct stiffness method. So this brings us already to the content of today's session. At first, I'd like to introduce you to an analogy between a truss framework and an FSAE steel tube frame. I will briefly touch base on the direct stiffness method just to show the theory behind. I will point you to some helpful resources so that you can get started right away after watching that session. And in the software demonstration, I'd like to show you how fast, easy and powerful that method is. But first things first. You all have seen a crane. And basically, a crane is a very good example for a truss framework. This calculation of truss frameworks is heavily discussed in civil engineering courses. But what I like to point out here is a truss framework is a very easy and determined system, and very similar to an FSAE steel tube frame. So just not saying that the direct stiffness method can't be applied to an entire steel tube frame, but just let me point you to a very simple example. Imagine this is your motor housing, and the suspension, rear wheel suspension is attached to that. Via the double wishbone suspension, you're introducing certain loads to your motor housing, which is displayed here as a truss framework. We have certain boundary conditions and certain forces. And maybe you're asking yourself the questions, well, where to put the stiffeners in order to ensure structural integrity of your system? And this is exactly a very good motivation to show you what you can do with a direct stiffness method, starting from a very simple approach, but getting to know very, very valuable information. As promised, some brief information about the direct stiffness method. I will do that with a very easy truss framework. You can see it at the left, just 3 trusses, truss elements, or some call it beam elements. In that case, a truss, you can imagine that as a spring, just a spring with a longitudinal stiffness. That's the most easy approach using the direct stiffness method, but it's already containing all the methodology. So let's have a look here. We have 3 truss elements numbered with Roman letters 1, 2, 3 and 3 nodes. At the top right you see a truss element. You see that each truss has 2 nodes, one at the beginning, one at the end. We have 4 degrees of freedom. That means every node can move in X and Y direction. So that is a very easy 2D example. The truss also has an identifier, and what you can see at the bottom right is the stiffness matrix of an individual truss. So this stiffness matrix is a 4x4 matrix representing the 4 degrees of freedom. As I've said, 1 truss, 2 nodes, each node has 2 degrees of freedom, so we end up with a 4x4 matrix, and the entries in that matrix are nothing but the elastic modulus of the material you've been using, so probably steel. You have the area of a truss, so the cross-sectional area, and also the length of the truss is important to calculate stiffness. Combining that to a 4x4 matrix, there you already have the stiffness of one individual truss. Another information that is very important, and I've depicted it here or I've given it the name connection matrix or ID matrix. It's a 2-column matrix with some numbers in it, but it's quite easy. You can just read it as the first line in that matrix is representing the first truss element. And which nodes are attached to the first truss element? That are nodes 1 and 3. And this is stated here. The same for number 2, truss number 2. Truss number 2 is comprised of node 1 and 2. Same for truss number 3. So the ID matrix is always a 2-column matrix, and the number of lines represents the number of trusses in your system. So as easy as that, you want to create the system matrix now. The only thing that might happen to the stiffness matrix of an individual truss is, okay, the truss is rotated, for example as truss 1 here. That means nothing but employing a rotation matrix to the stiffness matrix of your system. This means transferring the local coordinates to the global coordinates. And then we are already ready to go to fill up the system equations. So we have seen the local element stiffness matrix, and we want to put that in the global system stiffness matrix. This can be done via the ID matrix. The stiffness matrix of our system here is a 6 by 6 matrix because we have 6 degrees of freedom. Very easy, means we have 3 nodes employed, each with 2 degrees of freedom, so we have a 6 by 6 matrix. And depending on the ID matrix, the truss stiffness matrix or the element stiffness matrices become a certain place in the global system matrix. This is something that you can see here. Just putting the truss stiffness matrix, depending on their degrees of freedom and the IDs of the degree of freedom, to the right position. So then we have already assembled the stiffness matrix. Then what you see here is the displacement vector D. It says, okay, we have 6 degrees of freedoms, and some of the degrees of freedoms can actually move. That means, okay, 0 means this is restricted. Quite easy, we have node 1 and the degrees of freedom 1 and 2. That means, okay, that node may move in y direction, but not in x direction. Node 2 may not move at all, so it's a double 0 here, and node 3 is completely free. Then we introduce the load vector here, so we are applying a load pointing down to the earth on degree of freedom 6. And the following equation is already the system equation. It looks a bit like Hooke's law, and at the end it's nothing but Hooke's law, but for a 2D situation. We have the system stiffness matrix K, we have the displacement vector D, and the force vector F. And then nothing as easy as putting that matrices to MATLAB and solve for the displacements. After that, you can do some calculations to calculate the member force reactions, the reaction forces, the forces in the trusses. But this is already the direct stiffness method. By entering direct stiffness method to Google or any other search engine, you will find very good course material from all over the world in different languages. This is, let's say, a standard method when teaching finite element analysis. As promised, I would like to point you to some interesting links, and they are not somewhere on the web, they are on the MATLAB file exchange. I will get back to that slide in a few seconds, but first let me point to our file exchange. Let's start at the MathWorks homepage. Let's go to User Community, and there we are already at the file exchange. So what can I find here? So I just tried with truss or truss framework. Let's try truss here. And what comes up is there's quite a nice list of contributions from users that have faced the same problem. For example, what we find here is a guy showing a truss analysis for, well, obviously for quite complex systems. You have the files there. It's all open source. It lying under the BSD license. And as said, this is not just one entry. Just by entering truss, we get 20 entries. Some guys already talk about optimization. Some seem to have developed a GUI. Some already talk about beams, which are a bit more complex than truss elements. So there's quite some stuff available. You can search on your own, but what I also did for you is do a nice summary of that. So what I suggest is, if you have never heard about the direct stiffness method, just go to that link, Larry's Toolbox. Larry is a professor teaching in the US, and he has scripts that are very nicely documented. In the software demo, I'd like to show you something from that file exchange entry, but also the other links are really powerful. This is just an alternative. Well, take what you like. The next one is a bit more complex, as I've said, is also covering beam elements. So, as you say, a truss is just a spring. Beam already has a bending mode in itself, so you can bend that truss element. And the last entry here, the guy has already worked on optimizing a truss framework. This is not the only links that I've found, but I would say in the top to bottom range, just follow them and try to get used to the direct stiffness method a bit. And now it's already time to move to MATLAB and to introduce you what MATLAB can do. So I've worked a bit on that. I've taken a bit from the file exchange. I tried some of the methods. They all work pretty nicely. But as I've said, I'd like to introduce you to Larry's toolbox first. He has very nice examples. Just decided to pick that example here. He has a very clear scripting language. So what we see here, it's an example. We talk about an example with 12 nodes and 34 truss elements. Larry already introduced some loads. And what we see here, he calls the vector joints. It's nothing but a 12 by 3 vector giving the node coordinates. So I don't want to put it all down, but first node is at position x0, y0, z0, and then going down 12 nodes. The assembly is exactly what I've introduced you as connection or as an ID matrix. It says, okay, the first element is comprised of the nodes 1 and 2. And then again, he goes down and defines the 34 truss elements. He also introduces the load, which is nothing but saying, okay, which force is acting on which node. It's in that case 4 by 12 vector, and this is already it. Specifying some calculations at the end as the maximal force, and this is already the example. So let's just go through. Before showing you that plot again, just want to point you to the timing. That means run in time. And what you see here, we have a system that can be solved in less than 0.2 seconds. So quite impressive. Even if you have a steel tube frame with a lot more trusses, you will end up with simulation times around 1 second. Now doing it again, it's as promised a truss framework. Larry has attached it at the very edges and applied a certain load in the middle truss here. What we see here is the undeformed state with dotted lines and the deformed state with black lines. So now, well, I'd like to show you how easy it is to change that a bit, for example, in order to get a rotation, because you might be interested in the rotational stiffness of a truss framework. So I did nothing but take the load vector. I changed a bit, and what we have to do is nothing but changing that to the force vector here. Just plugging that here. It's a vector with 12 lines, just specifying the forces acting on each node, also the boundary conditions, that some nodes are constrained. What I learned, I have to reduce that significantly. Let's go down to 2000. And what we'll see, yes, very nicely, we see a rotational deformation. And what you could do is you calculate the angle between these two nodes, compare it to that one, and see how much your chassis deformed. So the main message that I want to bring you today is, it's quite easy to set up a truss framework. Just start from scratch, design the number of beams, take the coordinates from your CAD system, set up an easy model, and then you can already try to optimize a bit where truss is really helpful, where do they bring stiffness, or where they are just waste of weight. This is very easy using that method. What I would like to do now is just to go through the script that is called. Basically, what is done here. This is a function, and Larry calls truss tree.m. We will find that here. And what I want to show you is how easy the stiffness method can be coded. Larry gives a very nice information about his variables, so everything is clear, nice and readable. And if we go down, we see, okay, he's throwing some error messages in case something is wrong, in case your system is singular or some definitions are missing. That's also something that I recommend to you, because at the end you get error messages and sometimes you don't know really why. Then he's starting to set up the system. We see here that he's displaying the undeformed structure. That's done with the plot3 command. Then he calculates all the entries, puts them together in a system matrix. This is done over the next few lines for one member displacement equation, setting all that up. And what he's now doing is setting up the system equations, and at the end just solving the system. So within less than, I would say now we are line 200, a lot of that is comments. I would say in less than 100 lines you can get the direct stiffness method coded and then use it and work with it. But as said, it's no need to start from scratch with coding. Just go to the MATLAB file exchange. All is open source and you can use it right away. So now let's get back to our slides and to the key takeaway. Really, what's the important message for me in today's session is the KISS principle. So I've tried to show you an approach that is really short and simple. And this is also my recommendation for you as a team. If you're working on a certain problem, you have a limited amount of time, and the major rule should always be keep it short and simple. Second key takeaway of today's session is the MATLAB file exchange is a very powerful source of information. So not only for finite element analysis of your chassis, also for various topics. Go there, type your keywords, buzzwords there, and it's very likely that you will find the work of some guy, of a colleague that has already contributed to that. And last but not least, setting up a finite element analysis of your chassis just using MATLAB is fairly easy. I hope you liked the session. We are really keen on receiving your feedback via our team email address. It's formulastudent@mathworks.com. And for all other episodes of the Racing Lounge, just visit mathworks.com/racing lounge. Or for more information about our Formula Student activities, just go to mathworks.com/FSG. Thanks a lot for watching. I hope to see you next time. Looking forward to your comments on that episode. Bye bye.